Hello students, welcome to the channel Statistica Hub. So this is our lecture number 7 on the course SH201A. Okay, so in the last lecture we introduced you with something that is the random variable. We introduced you with the definition of the random variable, different type of like major variables. Now in this particular lecture we are going to cover something about PDF, PMF and CDF. So before moving to that particular topic like PDF, PMF or something like that, we have to understand different types of random variable. Okay, types of random variable. Now the point is like everyone know that we are having generally I'm going to cover like two different type of random variables. So we are having technically we have three different type of random variable. The first one, the second one, and the third one. So the first type of random variable that we deal with that is your discrete random variable. Discrete random variable. Then we are having the second kind of random variable that is your continuous random variable. So we have continuous random variable. Okay. Then we are having mixed random variable. Mixed random variable. So in this particular lecture, we are going to cover only these two parts. I will just give you like what is the meaning of mix, but that's all. This is the definition, that will be fine. Okay, moving ahead with this part. So I will again go back to the definition of the random variable. So what was the definition? So the definition of a random variable X, that was something like this, that it is some sort of function that is taking up values from the sample space and giving the values in the real numbers. So technically a random variable is a real valued function. Real valued function defined on sample space. Okay. Now I hope you remember like what is the meaning of support of a random variable. So again, I will go for support. Okay. So we have support of a random variable. So what was the support? If we try to recap, so we covered in the last lecture that we are having some random variable that will be taking sample space and getting value in the real number. So if we go for support of a particular random variable, then this support is nothing. This is just the range set of, this is the range of a random variable. That's it. Like if I say like we don't understand, like till now we didn't cover anything about different distributions. But if I just like, for example, if I take only this part that X that belong follow some Bernoulli distribution with some parameter P, then we know this random variable X, this can take only value 1 or 0. So we are having two possible values of the random variable. So the support for this particular random variable, if I say support of X, that is set 0, 1. So that's how we define the support of a random variable. Okay. Now the discreteness of any random variable or the continuity of any random variable, whether a random variable is discrete or continuous random variable, that depends on the support of the random variable. Okay. So I will give you like one definition, simple definition. So if support of a random variable, if support of a random variable is countable, then it is discrete random variable. Okay. And the second thing, if the support of a random variable is uncountable, then it is continuous random variable. Okay. And if you go for like the mixed random variable, I will give the definition at this place only. So if the support of any random variable is union of countable and uncountable set, countable and uncountable set. Remember, it is just the union of countable and uncountable sets. Then it is a mixed random variable. So that's how we define different type of random variables. Okay. Now let's try to understand like what is the meaning of this countable thing. Like how do we define or how do we get to know that this particular set that we are defining, that is countable set. Okay. So on that particular part, let's come to the countability of the set. Like how do we came to know that a particular set is countable? So I will start giving some example. So let's say we are having the first example, that is some example, let's say set 1, we are having some set 2, some set 3. Okay. In this set, I'm defining we are having 2, 4, 6. In this set, I'm defining 2, 4, 6, 8, and it is like never ending. Some sort of like this kind of number are there. And the third set that I'm going to define, that is a set that is from 2 to 6. Okay. So out of these three sets, we are having the first two sets. These two sets are countable. And how do we know that these two sets are countable? And this set will be uncountable. So we will understand like how we are defining that these are countable or uncountable. So for that one, you have to go back to the basic mathematics, maybe 6th or 7th grade mathematics. So when we understood different type of numbers, then we covered something about natural numbers. So we know natural numbers are also known as counting numbers. Okay. Now just simply go for this particular thing. If in a set, we can assign some natural numbers to the elements, then it is countable. Okay. Like this is not a very proper definition, but like to understand the concept, that works fine. Like you have to go for a proper definition, then you have to follow some particular standard book. Like this is like my way of writing something because I'm just explaining the concept. Okay. So I'm saying that we are having the natural numbers, and if you are given some particular set, and if all the elements can be assigned to some natural number, then this particular set is known as countable. Okay, moving to this particular part, I will take up the same example again, the set one that was containing 2, 4, and 6. So if I go for this set, I can see we are having the numbers in arranging like ascending order. I can simply say this is the first number, this is the second number, this is the third number. So with respect to each of the element, I am able to assign some particular natural number. And we are able to count them, first element, second element, third element. So countable set. Okay. Moving to the second case, the second example. In that one, I was saying 2, 4, 6, 8, and this process is like never ending. So what will happen in this particular set? So you can see this is the first element, this is the second element, this is the third element, this is the fourth element, and so on. So again, you are able to assign them some natural numbers, like this element is the first element, second element, and so on. And we know in this particular set, the numbers are not ending. You can go for like 8, 16, and so on. You can have like lot of numbers, maybe 10, 12, 14, such kind of series will be there. Okay. Now in this particular setup also, we are having infinite numbers. And if you go for natural numbers, they also belong to like 1, 2, 3, 4, and going to infinity. So we can say that with respect to each of the element in the set, there is one particular natural number that will be assigning its location. We can say in this particular sense. So we can see that the natural numbers that are coming from 1 and they are also going to infinity. The numbers in this sequence or in this particular set, they are 2, 4, 6, and so on. They are also going to infinity. So you are able to assign again some natural numbers. So this is also a countable set. So both the sets are countable. Okay. Now the countable set, it can be of two different types. So it can be finitely countable. It can be finitely countable or it can be infinitely countable. So what is the meaning of like finite countable or the infinite countable? So if we move to this particular concept, so if you go for the first set only, set one. So in the set number one, you can see you are able to assign the natural numbers to the elements, and the natural numbers, they're coming out to be finite. So this is finitely countable set. And if you go for the second one, we are able to assign the natural numbers, but they are going to infinity. So this is infinitely countable set. Okay. If I go for the third set, set 3, that was denoted like 2, 6. So we have different type of notations. So if you go for like this type of notation, this denote like it will take like individual elements. So you can see like whenever I'm using the curly bracket, I'm able to denote particular numbers, particular elements of the set like 2, 4, 6. Multiple elements are possible. But whenever I'm using this bracket or I'm using this bracket, the small bracket or the close bracket, the open or the close. So in these one, I'll be defining the lower bound, I will be defining the upper bound. Only two elements will be there. And all the numbers, all the real numbers that are in between them, they are a part of this particular set. So in this particular set, I can see we are having the number line. You will go for like 2. You will go for 6. So we are having this particular point. We are having this particular point. Now, if you start counting the numbers, maybe assigning the natural numbers. So I will say that this is my first number. Okay, makes sense. No issue in that one. But if I say what will be my second number, okay, so at the second position, if some student is saying, sir, 2.1, I will say no, you are having 2.01. Someone says, sir, 2.01, I will say no, 2.001, and so on. So you can see this process of finding the second number, this is not possible in the closed bracket case. If you are having the open bracket, then also you won't be able to find the first number also. You will say, sir, we are having like this is the open, so the 2 is not included. So maybe 2.1, sir. No, I will say 2.01. I will say 2.001 and so on. So this process is like never ending. Correct? So these type of sets, they are known as uncountable sets. And eventually any uncountable set that will be containing infinite number of points. So uncountable set is always infinite. Okay, so that makes sense. Like, how do we define different type of sets, countable or the uncountable set? Now, again, coming to the definition. So you are having any particular random variable that will be given to be discrete random variable if its support is countable. So it can be finitely countable, it can be infinitely countable. And in the second case, it is denoted to be some continuous random variable if its support is uncountable. Okay, moving ahead with this particular part. So if we go for like any particular random variable, then we define some particular kind of probability will be associated with that particular number, with particular random variable. Okay, so we are having two concepts. One is PDF, the other one is PMF. So PMF means to say probability mass function, and the PDF means to say probability density function. Probability mass function and probability density function. So if you go to these particular concepts, then technically for the discrete random variables, we define probability mass function. For continuous random variables, we define probability density function. Okay, moving ahead with this part, now we know this x random variable, that is a discrete random variable. So this x will be taking different discrete points, countable points. Maybe it is taking some x0 value, some x1 value, some x2 value. It can take like infinite values, but countable, some discrete points. Okay. So technically in this particular random variable, if we try to denote my random variable on the x-axis, so there will be some x0. Assume that we are writing them in increasing order. So this is some x0, this is some x2, 1, x2, and so on. Okay, if I denote the probability function on the y-axis, then you can simply say that in this particular part, the x random variable, this can take some particular value, some x0 with some particular probability. It can be any probability. Okay, but there will be some condition. Okay, I'll be defining that one in meantime. If you go for like any number that is in between x0 and x1, so that is not possible. That is the idea of the discreteness. There will be some particular points, there will be some mass at which the probability will be allotted. So in this particular part, there will be no probability in between x0 and x1. Okay, that makes sense. Moving ahead with this part. So once you go to the point x2 or the x1, there will be again some probability. There will be again some probability and so on. So this is how we define the probability mass function. So probability mass function is nothing. It is simply, you can simply write, we are having probability function of random variable x at a particular value x. That is simply probability that the random variable x is taking the value x. That is the probability mass function. Okay, some properties that you have to always remember. The first property, that the probability mass function this always be greater than equal to 0, because it is some sort of like probability function. So being a probability function, it will be holding the properties of a probability function. So it will be greater than equal to 0 for all the values of x. Okay, moving ahead, the second rule, that summation of probability function for all the possible values of x, that will be coming out to be 1. Like probability won't be like more than 1. Okay, that's how we are going to define the probability mass function. Now coming to the concept of probability density function. Okay, so think about like different examples that you can frame maybe. So if you go for like, okay, I will give some example. Okay, come to the next page. Okay, so we are having discrete random variable, we are having continuous random variable. Okay, so assume that like we can make one example. Maybe we are having some sort of necklace. Okay, necklace of beads, maybe some sort of beads or some sort of diamonds or something, whatever you can take. Okay, so if you are having some necklace, then there will be some kind of thread, and on the thread at certain particular values, there will be one bead, there will be another 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 bead. Okay. If I go for continuous random variable, then I will make another example. Let's say you are having some kind of maybe some river. Okay. So there is some river, then there will be some water that is flowing in this particular river. Okay. This kind of example, like we'll try to understand like how can we think about the probability mass function or the density function. Okay. Now just cut this particular thread from this particular point. So if I cut it down, then I will be getting the thread something like this. We'll be getting one bead at this place, another bead, another bead. We are having 5 beads, so I will make 5 different beads. Okay. Now the point is, if you are going to hit, maybe just take like a tip of your finger, and with the tip of the finger, if you touch it somewhere, then if you touch it at this place, maybe will you be getting any particular bead? So the answer is no, correct? But if you touch the thread at this particular place, you'll be getting one bead. So that means to say, if I say the chance of getting the bead that is not at every place, it is only defined at certain points where the beads are possible, where the beads are available. Correct? So that is the point of discreteness. For the discrete random variables, the probability is defined only at certain particular values or certain particular points where the X random variable is taking its values. So whatever places that are left out apart from these particular distinct points, at those points, the probability density, the probability function that will be coming out to be 0. Okay, that makes sense? Okay, so this is how we can think about probability mass function that is defined only on some particular discrete points. Particular discrete points. Okay, moving ahead and let's try to see the continuous random variable. Now, again, think about the same case. Like in this example, we had the idea, our goal was to get some particular bead. So like with the tip of the finger, you're able to get the bead. But if you go for the river, assume that you have to fetch some water. Okay. So is it possible that if I touch the river by my finger, then will I be getting some like water, any quantity of the water? So the answer that is coming out to be no. Like I won't be getting any water. Like if this is the flow of the water, and if I touch it with my finger only, then I won't be getting any particular like ml of the water. So that is not feasible. So to get the water, if this is the river, I have to go for some particular zone or some particular range that okay, I will collect the water in between my hands, maybe like this. That is the possible thing. So in the continuous case, we are going to cut it down. Okay, then only I will be getting this much water. So in this particular, the continuous random variable at certain point, there is no possibility of getting something. But to get something, we have to go for particular area. We have to cut down 2 particular points, and then we will collecting something. So technically, in this particular part, we define probability density function. At this particular place, we were having some mass, and we define the probability at that particular allocated mass only. In this one, there is certain area in which we are defining the probability. So this is probability density function. Okay, so that's how we define the probability density function. So it is denoted like f of x generally. Okay, and we are going to write like a particular kind of what we can say general rule for the probability density function. So you can simply say we are having probability that my x random variable that is in between a and b, this will be coming out to be integration f of x dx Okay, from A to B. That's how we define the probability density function. So this is the probability density function. So using the density function, you can define the probability of X being between two distinct points. Okay, so that's how we define the probability density function. So again, we are having the rule that probability density function, the fx at any particular point that will be greater than equal to 0 for all the values of x. But remember one point, at distinct point, the f of x that will be 0. That means to say, like, if you are going to integrate this one, if you say probability function a less than equal to x less than equal to a, so that will be integration a to a only f of x dx. So we are having the height, the f of x, you can consider that to be some sort of height, and this a to a, that is the length. So if the length is 0, the area will be 0, correct? So we have to define like two different dimensions to get some area. So in this particular example, when I say for the distinct particular point, then this point probability that will be coming out to be 0. The second rule, minus infinity to infinity, if you integrate out, this will be coming out to be 1, the total probability. So that's how we define the PDF and the PMF. I hope you're able to understand. Okay, moving ahead with the third and the last concept in this particular lecture, that is the CDF, cumulative distribution function. So we are having CDF, that is cumulative distribution function. Some people also write this as to be distribution function only. That's also fine. Okay, moving ahead. So this is some sort of function that is defined like this, f of x, that is probability that the random variable x that is less than equal to the small x. So we are having like some sort of cumulative probabilities. So if we go for a particular point, we add up all the previous probabilities. So that's how we define the CDF. So CDF is like a very important particular kind of what we can say topic or the point of interest. So we are having certain properties of the, so we have some properties of the CDF. So the first property you can think about, that is it will be less than equal to 1 and greater than equal to 0. Because technically the total probability that will be 1 only. So if you go for the maximum value and if you go for beyond the maximum value, then it will be taking the value 1. And before that one, it will be somewhere between 0 and 1. Correct? And if you go for some value that is less than that, then it will be 0 certain. It can't be negative. Okay. The second thing, the fx is non-decreasing. That makes sense also. Like if I say that my x is starting from this point, let's say this is A, it is ending at B. These are the possible values of x. So if you go for any value that is less than A, there is no probability. So the fx that will be taking a value, let's say this is my point. Let's say this is A, this is B. So before that one, if this is my fx, then this will be taking a value 0. Now at A, there will be some probability. So the probability will be like added up and it will be something like this. It will attain a maximum 1, then it will come out to be constant. So it will always be non-decreasing. It can't decrease, it can remain constant. Like if I go for this particular setup, I can think that in this between these two particular points, this is something constant. In the case of like discrete random variables, the CDF will form some sort of like step function. If you try to make up that one, it will be some step function. So it will be something like this, that it will be 0. It will be taking some value, constant, another value, constant, adding another constant, maximum 1. That's how it is being formed. Okay. Then if you go for the third property, the fx is right continuous. Fx is right continuous. So the CDF function that will always be continuous from the right. Okay. The fourth property that we can say, if you go for the limiting value, let's say x is going to minus infinity, f of x at this x that will be coming out to be 0. Because if we go on the left, then we know that we are having the x that can take values in the real numbers. Okay. But if you are approaching the lower end of the real line, then there may be no other possible values. There will be nothing like that. X is not taking any value. So in that particular range, if you go for less than or maybe towards the minus infinity, there will be 0. And if you go for the right side limit, x tending to positive infinity of the fx at some small x, that will be coming out to be 1. So these are some of the properties that you have to understand about, like how do we define the CDF. So CDF is like a very, very important point or very, very important concept that you have to focus on. Okay, moving ahead, we have certain rules, or we can say certain kind of relations. So we have relation between the CDF and PMF and PDF. Okay, so this is again very simple topic, very simple thing. Okay, so if I go for like a relation between the CDF and the PMF, so we already covered that part. How do we define the CDF? So we define the CDF like f of x at a particular value of small x. So this will be simply summation of the probability function. Okay, for which particular point, whenever my x is less than equal to the small x. Or in other sense, you can write this to be summation for all the values of, like, we can say whenever t is less than equal to x, we define probability of x at particular value of t. Okay, if you go for the relation between the CDF and the PDF, that will again be very simple. So if you go for like f of x at a particular value of x, then we just came to know that we are having the probability till the value of small x. So it will be simply like integration minus infinity to small x, and we are having probability function d. So that's how we define the relation between the CDF, the PMF, and the PDF. Okay, so you have to remember this thing. And we are having one more rule. If you do the d of f of x over dx, that will be simply coming out to be a probability function. Okay, so just remember these type of concepts. Okay, many times you'll be finding something like this. They may write fxx, that will be f of xx at dx. Okay, like you can simply see that we are getting the CDF by integrating out the PDF. So we can get the PDF by differentiating the CDF. Okay, so these are some of the relations about like PDF, PMF, and the CDF. And we just covered like how do we define different type of random variables, the discrete, the continuous, the mix, and we are having different properties about the probability functions and the CDF. So that was all about the lecture number 7. I hope you're able to understand. So stay tuned. Bye.